Alright, I'll see you next time.
Well, one of my friends is going to come later, so the Hispanic one to come. You talk to him, okay? I'm good friends with him. See ya.
Alright everyone, let's just get this charade over. Sorry, that sounds like a bad attitude. Finally, a true no-show Friday. No-show Friday. That's why I have videos. I understand your pain, why you're not here. Spring break, so I didn't figure many people would show up today. That's fine. Should we have a quiz?
Yep.
Yeah. No. Did I get anyone with that, by the way, you know, last time? Maybe a couple, I don't know. I do that every year. Okay, come on, folks. You gotta get through this and you get a week off to spend more hours at your work. Is anyone going to Florida? Or somewhere? Really? Kentucky? Why don't you just stay here? I mean, you're coming back anyway. Why go anyway? Should you be in your research lab?
Yeah, I'll be there every day.
No, I hope so. Well, anyway, okay, so yeah, I guess most of you aren't going anywhere. When I was in spring break, I was kind of important, so I thought, oh, come on, everyone. All right, so sorry, we're going to have to get through this. It's class business. I have a lot of stuff that hasn't been picked up yet, so then again, there's no one here, but I'll put it out anyway. And let's see, I got your homework set, and if you haven't seen it yet, your homework set, has a lot of problems you haven't seen before. I have partial volume questions, just because I have seen those on standardized tests. I saw it on the ACS standardized physical chemistry test. So, and I'll work some example problems in the second hour. And so I want you to see those, but I don't know that I would put them on the third test or level in the final. I definitely would not put those on the final. I didn't really cover them too much anyway. And, partial volume, 14 mils are added per mole of water to ethanol, remember all that jazz. So I had to, the homework's a little funky because I had to go back quite a bit before the third test. So anyway, I'll show you how to do those problems, and they'll be almost identical to the questions. Maybe on the third test, not on the final. I'm not even sure about that because I don't really care for those questions too much. Then you have the harder questions, so hard that you're going to need to use Mathematica to solve them. It's really not hard at all. And that's, this is why we have computers. I mean, back in the day, yeah, you had to pull out a slide rule. I mean, I can do quadratic equations, but cubic equations, I don't remember how you solve those. I think we covered them at one point in high school, and in higher order. I don't, you had to factor them or something. I don't remember. So anyway, what else to tell you? So anyway, I'll work that as well. We've got, all week to do it, so email me in trouble. Third test is the third test, then we have a week off in the final. Class is really winding down, so we're going to get into electrochemistry maybe today. After electrochem, we start doing all this random BS. The only interesting thing that comes next are phase diagrams. You engineers have already had it, but so you get to go to sleep. So chemists, when the engineers fall asleep, that's why. And that's kind of interesting. And then we start going into just all this random nitpicky stuff that's just incoherent, but it's standard, as much as I'd like to cover some weird topic, I can't put you at a disadvantage just because I don't feel like, teaching this stuff because it bores me. If it's on a standard test, if it's on an MCAT, I have to cover that for your sake. So even if it's outdated beyond belief. So understand this class gets boring. I hope you had fun. We've got 1 or 2 more days of entertaining things left, and that's kind of it. Also, this is really the last Friday that I'm going to have some stuff to do for you in terms of the second hour. Like, I'm asking some questions you haven't seen before. I have to go over that. This reactive delta G stuff, it's not hard. It's just once you know how to set it up. So I got to show you how to do that. After this, there's really not much to talk about next for Friday. So we'll do 346. things. I'll get you ready for that, starting with imaginary numbers. You have to get really good at imaginary mathematics. That's something actually I know quite well. So we're going to start covering that and some other maybe example quantum problems. Yesterday, your teacher was assigned, not me. It's going to be Robert Gordon, and I'm going to be back teaching Deacon 1 again. It's what I do. Look, folks.
Can you fight it?
It's a long story. I was obliged to teach Kid 340. I don't have a choice. So, of all the faculty that you could have after me, Robert is the most similar. And it's really the best thing that could have happened, to be perfectly blunt. And also, my notes are his notes. So when I started teaching this class, I got my syllabus, I got all the material from him. So I've been kind of teaching like him from the very beginning. Now, he does do a couple things differently. He has quizzes. I think so all right, he'll have quizzes, but he preps for the quiz. He actually records his lecture first. Then he does example problems in class. But I don't do hardly any, except sometimes on an extra Friday, and even then sometimes. He actually spends most of his time on example problems, and then you have the quiz, and he's basically already done it for you. So you got to come and do the quiz, and that's actually a large part of the grade, like half or something. I don't want to speak for him, but it's a very large part of the grade is the quiz. So just get ready for that. Just understand he's going to go over the quiz all week, and then he's going to give you a quiz. You take the quiz, you ace it, and there you go. You're set. So that's how his class operates. So anyway, so there was question.
You answer.
Okay. Any other issue? Question.
You said his name was Robert.
Robert Gordon.
Okay.
Yeah, he was just it's not 100% official, but yeah, 99% sure that's who we have. And again, of all the people who's similar to me, he's the most similar. And he really likes teaching his class, like a lot. Well, I guess I'm kind of nuts too, right? Because what you don't want is someone who's like, okay, I guess I'll have to do it. He asked to do it. Just like I asked to do this, so that's who you want, right? Okay, no other questions? We're set? Alrighty, so I think this will be I should get through this hour, and of course I have enough material for the next hour if you don't have questions. And I'll remind you okay, now remember that it is kind of important to keep this part straight. The circle versus not the circle. Remember, this is the Hess's law question from the table in the back of the book, and plus RT, LN, and again I use this weird notation that a lot of you did seem familiar with. And activities, stoichiometric activity, and especially today on your homework, I'm giving you gas phase reactions just for convenience. That's because for species A, that would be a reactant. We have this guy, and what's really great is that you can say that is a partial pressure of a pure partial pressure. So this little thing here works infinitely better for a gas. So remember, when we hijacked these gas phase equations for liquids, and we said that this is where we make a leap. Sorry, I should do it this way. When we say that the real partial pressure of the vapor in equilibrium with the powder dissolved in the liquid, and that's our reactants, that the vapor phase partial pressure reflects the molarity in the solution, is a giant leap that's generally pretty damn wrong. All right, in the gas phase, it's no more wrong than the perfect gas law, which is actually pretty good. So that's again, Dalton's law, which we had the second time in class. Anyway, so chemists, we don't care so much about how we set something up. If I have 2 moles of A reacts with 1 mole of B, then I'll start the question saying I mix 2 moles of A with 1 mole of B, just to make things easier, you're limiting reagents. And I don't care so much about that part. And seriously, when I'm designing a chemical reaction, and I know the stoichiometry, and usually I don't develop chemical reactions. If I do, it's kind of Mickey Mouse level because I'm a physical chemist. But when I do, if I know it's 2 and 1, 2 parts A and 1 part B, that I'm usually going to start that way. You don't always have to. To drive a reaction, sometimes you add a lot of A. If B is non-reactive, right, that increases activity of products, and that helps. We talked about that last time. The problem I have is that I have to remove the excess reagent. through some kind of chromatography or crystallography or something like that. And that can be difficult, and but at the same time, while it seems like I messed up my product because I've got a lot of reactants in there, if I don't drive a reaction, sometimes I won't get any products at all. So anyway, that's why sometimes you don't do things stoichiometrically. You synthetic chemists already know that, but anyway, just saying. So again, I don't care too much how the reaction starts. I care how it ends, right? And I know that this is 0 at equilibrium. And you don't have to write this down. We've already done it, and therefore delta reaction. Again, the Hesson's law question. Here, I'll do it like this, because this is how I'm going to do it more often. So I'm just doing a little algebra. And then we call this K. Big K, and that's generally the, what do they call this? Well, anyways, the equilibrium constant. Right, sorry, equilibrium constant is usually called K, and if it was the beginning of the reaction, we call it Q, and that's coming up under the electrochem. All right, then we talked about where did we end? The example we did. I was kind of rushing last time, but you want to get your homeworks back. Was sorry, I'm a little bit lost. A goes to 2B. Sorry, what am I doing? What am I doing? A, and when I wrote 2. And again, sticking with gases. And I'll actually do the reverse. 2A goes to 1B in the next hour, just so you know. I don't want to make the same example over and over again, because then if that's not like what I have on the test, this will clearly be on the test, by the way. On the third test, and likely the final, because this is one of the better things that we do. Okay, so this gets squared, and again, that's because of the stoichiometry right there, just right there. And A star over PA. Okay, and that's to the first power. And so anyway, then the next thing that we went over was that, again, these numbers in the table in the back of the book have had all kinds of tweaking. I don't know how they measured them. Sometimes they measure what those numbers are at SDP. That's great if it can be done, but it often can't. So you have to, if you want to talk about water disassociating, it's just not going to happen at STP. So they put it under conditions, they heat it up, let it dissociate, put it in the calorimeter, make all your measurements, and then you mathematically go backward and say, well, what would I measure if, by some miracle, this did work at STP? And so all the numbers have been tweaked. So, and that is to say that the partial pressures have been tweaked as though they were 1 bar. So it's kind of nutty that we did that, and I hope that's not kind of confusing. The point of us having done that is that those numbers in the table on the back of the book are infinitely useful. It makes it easier to use those numbers than if they had not done that. It sounds like, oh, why did they make it so complicated? So that it would be easy for you. All right, because now these numbers are 1. Especially, when I see something get squared, it makes me nervous. And it should, by the way, at least this part didn't get complicated, these parts do. And the last thing we talked about was what happens to the real pressure. Now, this guy is apparently invariant to pressure because this guy was done at 1 bar. And I have to admit, that does kind of confuse me, and I'm going to try to work it out through my head, just hopefully for now you can accept that. I don't like asking you to do that, but if this guy is defined and is pressure invariant, then so does this one have to be, I think. That still just bothers me a little bit. I'm going to work on that over the week. So if that's the case, then, here, let me, well, yeah, if that's the case, I'll work a more concrete problem in a little bit. That means if I was to increase pressure to keep K constant, here, let me just simplify it. Oh, and by the way, we often abbreviate 1 bar as this. Again, standard, that always means standard pressure, 1 bar. So anyway, let me simplify this so it was obvious. P squared over PA, real partial pressure. Okay, so now if I say, since these are gases, if I say that these partial pressures are mole fractions times the total pressure, Dalton's law, then I can see that I end up with total pressure squared divided by total pressure. So that means that K is a function of the pressure, but it can't be. So if pressure goes up, that means that the mole fractions have to be altered. And again, I'll write out a little concrete example. So if the pressure goes up, K wants to go up, but it can't. That means the mole fractions will go down. That means the mole fraction of B goes down. That means equilibrium shifts to the left. So here, let me just go linearly. I'll be more explicit. I know I'm just being hand-waving that right now. What will happen is that equilibrium shifts to A. Equilibrium will shift to A because, again, this Le Chatelier's principle, and you are going to do it on your homework. You're going to mathematically prove Le Chatelier's principle is correct. I'm going to show you how the next hour. And it's obvious. You've perturbed it, it always fights back. That's Le Chatelier's principle. If you try to drive it, it always tries to resist, and that's pretty sensible, especially if you have cats at home, especially naughty cats. So if I increase pressure, the way to stop, to not allow it to do that was to go this way, produce less gas, less pressure. So it's perfectly sensible. All right, now let me give you concrete examples, and then I'll explicitly start including pressure, because right now I've been very hand-wavy about it. I'm just trying to be easy into this. And this is part of your homework. This example is the Haber process. We've done this a million times. It's ammonia production. I'll stick to this example for 342, and then I have something else, something about urea or something like that for PChem for biochemists. And I should be more explicit. If I'm talking about where does the reaction stop, I need to be doing these double arrows to show equilibrium, so I've kind of screwed that up a little bit. But again, second most produced chemical in the world, so pretty relevant. If you can discover a better catalyst, then I think they use nickel for this. If you could find a better catalyst, you would be the richest person on Earth. And all these are gases. Yeah, I think I got that right. All these are gases. So let's build K, and we'll I think I will definitely have this on the third test. Give you something and then say, okay, if pressure goes up or down, which way does it shift? And prove it. I mean, you can just kind of look at it and tell that obviously I've got more gases on the left but on the right than on the right. But let's prove it by actually getting K. And then that will segue into actually plugging numbers into those partial pressures, which you do on your homework to give me real numbers. Okay, so K, let's see, I've got to have products. I'm going to not put it at the top or the bottom. I'm just going to go ahead and write it all out linearly. NH3, why did I keep that? Okay, and so I know that activity has to have partial pressure over pure partial pressure, but that happens to be the number one. But I'm going to keep it there, and they're both squared because of that too. All right, I'm going to go ahead and write these out like this. It's just I got to flip them, and sometimes I screw that up. So be careful if when you're doing this, that this guy is normal and these guys get reversed. H2 squared times PO. N2, and nothing squared. Okay. Q. What's that? Q.
H2.
Yeah, thanks. Yeah. Writing and talking at the same time doesn't work too well. Okay, so let's simplify it a bit. P, well, I've got P and H2 and H3 squared. That looks like I've got PO. So we've got the chip on the right. 4, 2, okay, PO squared, and P, H2 cubed, and P, N2, and there we go. Okay, so now Dalton's law, and that means that I'm going to say pH2 is the mole fraction of H2 times the total pressure. Okay, so I'm not just doing it for this one. I'm not going to write them all out because that would kill my arm. Okay, so now K is, let me read my notes. Okay, no, this isn't hard. So that'd be chi NH3 squared over chi H2 cubed chi N2. And I'm going to keep the pressures over here. Now I got PO squared, and here's the thing. Without trying to just do it in my head or write it out, I know that this has to be canceled. But I know that the actual pressure shows up there. And then this is a constant. So the way that this gets expressed is to say that there's two different types of K. There's a K is equal to this total. There's the mole fraction K. Then there's this thing, which doesn't do anything. You just always ignore it. And on the test, if you just drop it instantly, I won't care, because that's fine. It's 1. Just remember, always keep pressures in bars. Kind of like when we did P equals nRT, I said, my thing, kilopascals and liters. All right, so in this case, do not start working in kilopascals, work in bars all the time, because that's just how they did it. Okay, so again, let's say that if pressure was to have doubled, it's always easier to think of going to higher pressure, because that's always for a human easy. So if pressure doubled, this is now 1/4. So K has apparently gone down. But K can't go down. So K, this part has to go up. So if pressure goes up, this has gone down, so this has to go up to compensate. And let's see that. If this goes up, this goes up, this has to go up, and this has to go down. So obviously, if I increase pressure, I'm actually favoring the product. And again, if I have this on the test, I will be more explicit that this is what I want you to do. I kind of screwed that up a little bit on the last test, which I'm going to go over the last test just for a few minutes before we get into the homework. It's certainly worth partial credit to say, well, if you pressurize it, it's going to want to depressurize, and the way to do that is to make less gas. And that would be correct. I would certainly give lots of partial credit, but I would really rather see that you know how to do this. Besides, it's going to be, the next hour, we're actually going to start putting in numbers, and that's going to be part of the test too. That'll be one of the hard questions. In fact, I may get rid of the derivation, which I think you'll like. I think you'll like, and instead do one of these where you actually have numbers, which I'm going to do right now. So one less derivation is what I'll do. So question.
So you said that when pressure goes up, the mole fraction of the product will go up while the mole fraction of the reactant goes down. Will there be such a question where we have to see which of the two reactants would decrease more than the other?
Well, now you can't do that. For every 3 of these, you lose 1 of these. Right. Now, if that got monkeyed with, then total mass is being monkeyed with, which means you have a nuclear explosion on your hands and everyone's dead. Right. So yeah, just atoms dictate that is going to behave itself in exactly a 3-to-1 ratio.
Okay.
So yeah, but it's fortunately not that tricky. So now let's do. I know I've been very hand wavy the whole time. Let me do an example where we're actually going to start getting numbers in. And so I know that this will sound kind of horribly complicated, like, you're given a reaction and now you have to tell me how many products are formed. And the high schooler in me would say, well, I have no freaking idea how to go about that. But there's this little system, the little methodology I have that I think is really easy. Again, I'll go with a different example. Dissociation of water into hydrogen and oxygen. So you can imagine the thermochemistry of this is known. Well, you can look at the table in the back of the book. Right? This is the reverse formation of aqueous water. That number's in the table in the back of the book. There's no way they actually put that number. That number was not measured at STP. That is impossible. They must have gone to a couple of thousand degrees. And again, then they took heat capacities and then figured out, shaved off what that temperature, how that temperature affected their measurement. There's no way they could have done this at STP. Okay, so now I've given you this thing, and now I wanted numbers. I'll give you a delta G naught. Again, Hess's law question, I won't even have you do that. It will actually just be the formation delta G of this. It would be the same number. And then I'm going to ask how far does this reaction go at STP? And here's how you do it. Okay, first thing I do is I make a table. I put down all the characters. I start with reactants, products. And then I say initial. So if I had 2 moles of H2O going to 2 moles of H2 and 1 mole of O2, I would usually put 2 N here, but I'm starting with 1 mole, so I'm going to put N. And I don't have any products. Final. Okay. We're going to introduce that extent of reaction. It's traditional to call it alpha as opposed to that epsilon I used before. That's how it does it, so I'm going to stick with that. Now this is phenomenological, but it is fully correct. Because of conservation of mass. When alpha is 0, I better have N of this. When alpha, because no reaction periods, alpha is 1, this better be gone. So I just have to figure out the function that does that, a function of alpha. N, no, I gotta start with N, and it can't have alpha in it. Because when alpha is 0, I better have N moles. So now I'm going to tack something on. I'm going to subtract, because that's sensible, because it's a reactant. What do you think I should subtract?
The extent.
Extend times,
Coefficient. Stoichiometric coefficient.
kind of, you're getting close. Remember, I have to end up with 0. When alpha is 1, this better be 0.
Extent times 10.
So alpha times, right, minus alpha n. There you go. Alpha 0, I have n, alpha 1, I have 0. Perfect. And it's fully correct. It is well, couldn't it be a complicated function? No, that's like saying, again, atoms are atoms. They don't just disappear or create. So this is actually 100% correct. I'll gain n alpha of H2, because if I've lost a mole, I gained a mole. And this one's a bit of a bismuth. Right, half a mole of oxygen. All right, now, stop. Totally. Again, this is the algorithm. Write the table before, after. You don't really need to do before. It's kind of obvious. But I think it helps you if you have trouble. If you have trouble with this, I think this kind of keeps your head thinking correctly. Now, we'll add all this up. N minus n alpha n plus n alpha, so that wipes that out, plus 1 half n alpha. N plus 1 half n alpha. Why? Because the next thing is mole fraction. Number of moles divided by the total. N minus alpha n, and plus 1 half n alpha. N alpha over n plus 1 half n alpha. N alpha over 2 plus n alpha. I took care of the half, right? So you can see that. And okay, so then what I would do to build the K table. Okay, this is all you really need for the K table. Let me do one more entry. Let me do chi again, because I can see that those n's are all actually going to go away. You see that they factor. Sorry, my handwriting is small today. You see that? You see how I can factor in and out of all of these? There you go. Oh, sorry, that's awfully small. Hopefully you have trouble just video it, right? Okay, now I'm going to use that the partial pressure of, and now let's stick with H2, will be P times chi of H2. Right? And et cetera. Okay, now I can build K from partial pressure over P naught, which is one which I don't even really need to include it. Okay, but I'll be very explicit about it. Okay, so K, let's do activity. We start at the very beginning. Activity of O2, H2, so I'll do H2 first. Activity of O2 the half, I mean the activity of H2O. Okay, that's normal. Okay, now this is going to be mole fraction of H2 times the total pressure times the mole fraction of O2 times the total pressure, the half, over mole fraction of H2O times total pressure. Now, I need to take care of my P naughts, and I can tell you that that is going to be let's say P naught. No, sorry. Let me take care of these guys. That's going to be P naught to the 1/2. I'm dividing. Remember going reverse. It is a little bit of a pain. Okay. Now, yeah, it is a little tough. And if you look at the homeworks, I actually do walk you through a lot of this in the question. The questions.
In the initial X, how come it's 2 plus n alpha, not 2n plus n alpha? On the second X column?
On here?
I'm sorry, row. Sorry, so the next one over?
This one?
One down,
Okay.
and then all the way to the right? How come it's 2, no, one down again?
I know, 1/2. 1/2. I took the bottom, I took this, I took the total, and multiplied it by 2. Shouldn't it be
2n. Is it 2n plus n alpha?
This times 2 is oh, yeah, sorry. sorry. Yeah.
Okay.
Oh, okay, sorry. It's a little, when I make that obvious kind of mistake, it's really just a mistake, so I was right about that, yeah. Now, I can also assure you that there is never a case when you're dealing with this table, the ends always cancel. It is impossible for them not to cancel. I could never come up with a complex reaction such that these mole fractions don't come out in functions of alpha. It has to be that way. So, yeah. I know this is kind of painful, it's been pretty long, but it's very formulaic. If you have trouble, watch the video. And I'm sure I have a handout somewhere, so I'll double check. I forget about all the handouts I have. Okay, now let's insert this. Okay, so that's, where am I at? Okay, I'll start. I guess normally I like to start with products. I'll start with reactants. I got to remember I need to flip this guy over though. Actually, hold on. I'll start. What am I doing? I'm being an idiot. I'll start just like this. So I have alpha. I'm doing H2. Alpha over 1 plus 1/2. Alpha over 2. I'll write it like that. And I've got to remember pressure over P naught. Now, I've kind of already done that, but I'm just being very explicit. Okay, now, O2, so alpha over 2 over 2 plus alpha, 1/2. I've got pressure, the 1/2. I've got 1 to the 1/2, which is 1. And then I've got H2O. Okay, now don't forget this. This is how you're going to miss this. 1 plus alpha over 2. I'm flipping it, right? Because it's a reactant. That's the thing that'll screw you up. And on top is 1 minus alpha. That's alpha. That's right. I've got P over P naught. Right. So you've got to remember, guys. This is terribly important. Remember to flip the reactants. That's the thing that'll get you. So I can tell you that I know that this will, let's see, pressure the 1/2. Okay, so I've got P to the 1/2. I've got P naught to the 1/2. And I know that automatically, I don't even have to think about this. Okay, then I've got alpha to the 3/2. Okay, here's something. You don't need to do this. This, I'm going to cancel this out. Always look for that. Those denominators, those denominators, the total moles in the mole fractions, they're going to cancel each other out because they're common to all of them. So just be wary of that. So that leaves me alpha to 3/2 on top. So don't screw up your algebra. Alpha to the 3/2 on top. And then I've got 1 minus alpha. And left over is 2 plus alpha. not going to go further with this because I'm going to do it in the next hour. This is minus delta reaction G. Not. Sorry, this is all to the E power. Let me start there. Sorry about that. Delta reaction G naught over RT. Okay, so in the next hour, when I actually work some numerical problems, I'm going to give you this. That gives you a number here. And then this will be 1, right? So this is gone. And this one, I'm going to give you traditionally, in most PChem textbooks and example problems, you say that this reaction is carried out at 1 bar. And so I'm seeing that we're definitely gaining moles. So what you'd have to have in this mousetrap is water, and by magic it'll be doing this at room temperature, in a box that can expand to account for the increase in pressure, to keep pressure at 1 bar. So in other words, in traditional PChem classes, I'm going to vary this a little bit, this is automatically 1 by definition, and we'll keep this at 1 even if we do it by magic, leaving you an equation with one unknown. You have a number, and you're looking for alpha. So all you got to do is solve alpha. Right? Right. It sucks, doesn't it? Right, there's no simplifying this. Well, I mean, yeah, yes, it can be simplified, whatever. But not simplified since that the answer is very easy. And I'm looking at this like, so again, this guy's gone. That's like 5 or something. And I'm thinking I already want to square it to get rid of that. Well, I hate equations with square root, so I'd square both sides. Then I would simplify it. Then I'm going to have alpha to the third. I'm not even sure what to do. What you're going to do is you're going to go use Mathematica. Mathematica is so freaking awesome that it doesn't like alpha, it likes x, all right? You just write this out equal to this, and you hit solve, and it says x is equal to this. And that's how you do it, that's fine, that's why we have computers. Now, but continuing on with this, let's call this the KI, because I'll do numerical problems next. I'm not doing it now, I'm trying to do this bit by bit. So now we're going to say K is this K alpha e to the 1/2 divided by 1. It doesn't matter. And where K chi is equal to that alpha to the 3/2 over 1 minus alpha 2 plus alpha to the 1/2. Now, if I plot that K alpha versus, the mole fraction part versus the extent of the reaction. Now, I'm going to draw this like a box because it goes from 0 to 1. And I actually had to use a MATLAB to do this. And I saw what it does is this. It goes off to infinity. That doesn't look so good. Anyway, it's going to go off to infinity because that's going to be 0 and it's not really compensated anywhere else. Now the question is, pressure has gone up a factor of 4. And again, this will be one of the easier questions on the next test. Pressure has gone up a factor of 4. How much? Yes, you see, I have to learn how to write better questions, especially on the second test like I'm going to talk about. I felt like a lot of your problems is because if I worded the question a little bit better, I think you would have had an easier time answering it. So I kind of feel bad about that. Not too bad because I'm a monster. But okay, so you're on the test, and I've given you that reaction. I said, now show me explicitly what happens if pressure increases. And I mean to do this. I mean you to do this, right? And instead you say, well, pressure increases, therefore equilibrium shifts left. Right? You know, because there's less gas. All right, partial credit, but I said, please show me prove it, you know? How could I have worded it such that I would have made you do it the right way? Pressure goes up a factor of 4. Tell me how the ratio of mole fractions go down. Right? Now that forces you to really look at this. So if this goes up a factor of 4, then this K chi has to go down by half. Right? So now you've proved it to me. And you couldn't have answered that unless you had done exactly what I wanted you to do. So I learned things in this class too. Okay, if this goes up, that goes down, and I'm looking here, if this goes down, I'm turning this graph on its side, if this goes down, alpha goes down. Right? And that means that there's less H2 and O2, meaning equilibrium can shift left just like it should have. So there you go. So anyway, the important thing is that be able to do that, all right? It's kind of horribly important. Last bits, and then maybe we'll break a little bit early and come back again. Going to go over the test first. I know a lot of you aced the test, but it's review. It will help you get into my head. I am writing the test after all, so the better you can think of, get in my head, the better you can predict. So I'm going to start with going over the test, and even though you got an A on it and you're going to squirm, I'm not going to do it last because then you're just going to leave. So I'm going to go over the test first, and then I'm going to do the example problems. You have to see this, right? It's very important because I really haven't gone over these questions in the other way. So now let's switch gears. And again, we're not dropping this. I'm going to spend most of my time on this in the next hour. Let's switch gears though, and then because Monday next, when you come back, we're going to be on electrochem. And I think that's no more than 2 days to maybe 1 week. Electrochem what's interesting is that, like when we're doing these reactions, because we're synthetic chemists, I don't care how it begins, I care how it ends, right? Because that's my yield, and I really only care about yield. When it comes to batteries, then you got this last time. How much juice is in the battery at equilibrium? Now you hold it to your tongue like you were a kid, because for some reason that's funny. Right, it's dead. Equilibrium, there's no electrons. So when it comes to batteries, and batteries again are important because of how we think our energy economy is going to go, which isn't true, but that's what we tell ourselves to feel good and not be afraid of the future where there's no electricity, that we're going to have photovoltaics, we're going to cover Arizona. If we cover Arizona, we all have enough power. Anyone been to Arizona?
It sucks.
It sucks. I'm surprised I like the desert. I really like the desert. There is no way in hell we're going to cover Arizona. That's impossible. That place is freaking huge. But we're all going to tell ourselves that's what we're going to do. And at night we're going to run on batteries. And that is the idea of how we are not going to run into a catastrophe of CO2 in the air. It's not true. We're going to burn coal. We have 2,000 years of coal left until the coal is gone. We will burn it. The problem is that our sky will turn black. So we can't have that. That will kill us all. We simply cannot do it. So we're going to have to scrub the coal. We can already do that. And everyone's like, oh, clean coal technology. We have clean coal technology. It's just expensive. So will your power. It will be so expensive, you can only afford to cook a little bit. No television, no computer. You simply can't afford the electricity. And, God, I'm sorry. That's horrible. But anyway, that's okay. Okay, so let's do that. Now, I said already that pressure doesn't count for the reason I stated, but the equation which okay, I got T right here. Okay, so temperature does change things because it's explicit in the equation for all of this stuff. So if this guy's changing, obviously my K is changing. So K will change with temperature. So we have to figure out what that is. All right, so I'm going to just write down the same old. Oh, sorry. I already wrote this down. I just wanted to make sure you see where it comes from, so you don't get lost in your notes. Again, we're going to be at equilibrium because for real reactions, I want to know the yield. So I've got minus delta reaction G over RT. Okay, now we're going to be getting into a lot of this. I want to see how K changes, but I don't, I have my K here, and I have a nice simple thing here that I can solve in a minute. I'll show you. But I've got a natural log of K. So I'm going to live with that. Natural logs are actually rather linear. So what I want is the change in natural log of K with temperature. This is the question. Now, if I can figure out how the natural log of K changes, that's as good as knowing how K changes. I just take that number and raise it to the e power. It's very easy, right? And as much as this seems like I've complicated the question, I really haven't. I've decomplicated it because this is minus 1 over R, change in delta Somebody? You've already done this. Don't you remember it? Yeah, right. Gibbs Helmholtz. We've gone over this. Remember I told you, we did that a while ago, and I said it was going to come back a couple more times. And we're actually going to see this a hell of a lot, by the way, especially when we do phases, which is still kind of interesting, and then it gets kind of de-interesting. Okay, minus 1 over r, and I have to kind of remind myself that it's minus delta h over t squared. So rt squared. Sorry to write over my own derivation. I know it's kind of annoying. Okay, now, okay, so we're getting pretty much on time. So now I have to. I'm not even gonna do the algebra. Bring the t over. Sorry. Sorry, this is kind of funky. The change in the natural log of k is equal to delta reaction h naught over r t squared. And as before, I'm going to make the approximation. I'm not going to let this change with temperature, and that's wrong, but I don't also want to really horrendously complicate things. So I can certainly calculate how h changes with t. So I have a function of t in here, and then I need to integrate it. Just to get the point across, that's not so necessary. I don't care to be super accurate sometimes, as long as you get the gist. Just as one of those times. So remember, I'm making this constant. Okay, now remember, one of the important things you always got to know about calculus of things that are real, is that the limit has to have the units of whatever the heck it is you're integrating. Sorry, the partial of what it is you're integrating. So this has to be ln k1 at t1, and this will be ln k2, which is the k at t2. So what you end up with is, okay, I'm going to solve it, and this is so trivial that I'm not going to be very explicit. This is going to be ln k2 minus ln k1. So we're going to keep this over here. ln k1. Okay, now this guy, 1 over x, the derivative is minus 1 over x squared. And I've got a 1 over x squared, all right? But I picked up a minus, so I'm going to have to add another minus. Minus delta reaction h naught over r. And then I've got 1 over x, but I've got limits of x2 to minus x1. All right, and those are actually temperatures. Okay, very easy. Okay, so now, now the question is, let me just do one little simple thought question before we bolt out of here. If temperature, it's always easy to think about temperature increasing. We're kind of naturally prone towards thinking like, well, let's heat it up. You know, like, let's burn someone's house down. Let's not freeze it down. Be kind of chef from South Park suggested they freeze, don't freeze. Anyway, all right, so we like to heat things up. And I want to know whether K2 increases. All right, so K2 minus K1, ln K2 minus ln K1. If K2 gets bigger, then ln K2 gets bigger. All right, so I know that ln K2 minus ln K1, if it's positive, then that means I've got more product. And that's what I want. Of course, why am I even asking that? Okay, so if that's true, then this has to be positive. This whole thing. All right, so we break that down. T2 is a bigger number. We always, again, that's because I like to think about heating things up. 1 over a big number minus 1 over a small number is negative. All right, if I'm going to heat it up, this term is always negative. Now, negative times a negative is a positive, which I want, as long as this is also positive, but it can be negative, right? If it's positive, then heating will cause K2 to get bigger, which means more product. It's, no matter how complex these things get, that will always mean more product. Okay, so if H, delta reaction H is positive, is that endothermic or exothermic? Endothermic. You always heat an endothermic reaction, and you cool an exothermic one. There you go. All right. Break time. Got to juice the camera. Back in 10. And you want to stick around because you really need to see how to do those